Okay, the standard score, or z-score, getting adjusted by the sample size that we use. Okay, and this is 7.2. We talked a little bit about this in 7.1, and now we'll do a few word problems to kind of show it a little more clearly. So the mean cholesterol level for a person 20 years old is 197. Okay, what's the probability of someone having less than 183 if the standard deviation is 35? Okay, this should seem familiar from back in chapter 6. Okay, here's our mean called mu, and our deviation is used to get our z-score. So we take the score we're interested in of 183 minus the mu, or the mean, over the standard deviation, gives us a z-score of negative 0.4. That's how many deviations. So we're just under half of a deviation to the left. Okay, and then we can use our table or calculator to get the z-score that goes with that. Okay, so we look at our z-table, negative 4.00 is area of 0.3446, or just over a third of the area. So that tells us about a third of the people would be below 183. The other 2/3 should land above 183, again, based on a mean of 187 and a deviation of 35. Okay, now that should look familiar. Now, what's the probability of picking a random sample of 25 people, adults, and having that group with a mean less than 183? Okay, so we picked one individual, and the chance of being under 183 is a deviation of negative 0.4, an area of 0.333446. Okay, I'm trying to talk too fast. Now, what if I pick 25 people, take all of their cholesterol numbers and average them together, add them, divide by 25, what's the chance of that number being less than 183? Okay, now what happens here is if I pick a good sized sample, average those people together, that number, the mean, should get pulled toward the center. Okay, because we got a few people way out there, but the other people on the other side are going to bring their scores to bring them in, and they kind of all pull everything to the middle. So the it's going to basically change our deviation. Okay, so here's what we do. The sample size n is going to take our standard deviation of sigma, and we're going to adjust it by dividing by the square root of n. Okay, so the bigger the sample size gets, the bigger we're going to divide by, and the smaller our deviation is going to get. Okay, and this is called sigma for x bar. Okay, so the sigma of our averages as our data points. Okay, so our averages of each 25, those are our data points. So sigma of our averages is going to be the original sigma divided by the square root of n, our size of our averages. And here's how that's going to adjust it. Okay, n is 25, so the square root of that is 5. That's our new sigma for our sample size of 25. Okay, sigma for the sample x bars is the original 35 over the 5, and we get 7. So our new standard deviation is 7 instead of 35. Okay, so that's going to represent our bell curve kind of shrinking together. Instead of jumping out by increments of 35 for every deviation, it's only jumping out by increments of 7 in each direction for each deviation. Okay, so I'm going to calculate my new z-score with my 7 underneath there, and that's going to adjust the z for my 183 is now -2 deviations to the left, because my deviations have gotten so much smaller. 183, instead of being only 0.4 deviations, it's now 2 whole deviations to the left. Okay, and in other words, the chance of getting that low is 0.0228. There's only 2.228% of the time will I get this low of a number because I'm averaging these together, and I'm expecting my averages to really shrink toward the middle. Okay, trying to describe that the best I can, but because I'm taking sample sizes, my deviations are a lot smaller, and any particular number like 183 is now farther out there and a lot less likely to happen because my numbers are going to be so much closer to the mean. Okay, hope that's clear. Okay, so just interesting to compare these from -0.4 to -2 deviations. 183 is way out there now and much less likely to happen. And so again, our conclusion is slim chance of getting less than 183 when I'm averaging all these together. I'm expecting numbers much closer to the mean. Okay.